distributions. All right, so first a review of normal distribution. It's a bell-shaped distribution with, it has a mean of 0 and then a standard deviation of 1. So shown on the right, you see the mean and the standard deviation, and you see that most of the statistics are in the center of the distribution, and then there's some on the edges. It's also known as a z-distribution, and 100% of the observations fall under the curve, which just means that there's no observations that are outside of the curve here. So the central limit theorem is just states that if the sample size is sufficiently large, then the sampling distribution will be approximately normally distributed. So as you saw before in the image, that the larger our sample size, the more normally distributed it will be. So in other words, the more people or cases we have, the more bell-shaped it will be, more centered. And then a standardized score is also known as a z-score. This is just a review from previous lessons. Is just the distance between an individual score and the mean in standard deviation units. So using the normal distribution, you can use it in hypothesis testing and confidence intervals. First, we're going to talk about hypothesis testing. So there's a 5-step hypothesis testing procedure. It's a little bit different from the randomization test, but it's kind of the same idea. So we're going to walk through an example of it, but the steps are that you check assumptions and write hypotheses, then you calculate the test statistic, then determine the p-value, make a decision, and then remember to state a real-world conclusion at the end. So we're going to go over an example of it. So we're going to go over an example after. But a normal distribution, there's just the normal distribution method, which is just saying that if the sampling distribution is normal, we have a normal distribution and the mean is equal to the parameter, the hypothesized parameter, which is just the number in the null hypothesis. So that is equal to the mean. And then the standard deviation equals the standard error. And then that's how you can find the p-value through, which we're going to see in the example that we do. And then with that standard normal distribution method, we find a z-score, and then we find the test statistic. So when using the standard normal distribution method, the test statistic is standardized. So you'll find the z-score by taking x minus x bar, and x is just the average mean that we're given, and then x bar is our statistic, and then you do find the difference between those, and then you divide by the standard deviation. And then when you're conducting a hypothesis test, the sampling distribution is centered on the null parameter, which is just the number in the null hypothesis, and then the standard deviation is similar to the standard error. So therefore, how we calculate our test statistic is the sample statistic minus the null parameter, which is the number in our null hypothesis, and then we divide that by the standard error. So we're going to walk through an example of finding it with using the hypothesis testing. So are more than 50% of all World Campus Stat 200 students female? So data were collected from a representative sample of 501 World Campus Stat 200 students. So our N, or our sample size, is equal to 501. And then in that sample, 284 students were female and 217 were male. So if you want to refer back to the data, I put it on the top there for you so you can kind of connect it. So we're just going to go through each step of the hypothesis testing and just apply it to what we're given. So step 1 is to check assumptions and write hypotheses. So we're going to look at the data that we're given and write hypotheses based on that data. So we know that we're looking for a proportion, because we want to know if the proportion of Stat 200 students that are female is greater than 50%. So our null hypothesis then would be 0.50, p equals 0.50, and then our alternative would be p is greater than 0.50. So our next step is to calculate the test statistic once we get that. So first we calculate our p-hat. So p-hat is just the proportion of females to the the rest of the proportion of females in the group among all the students. So it'll be the total number of females divided by the total number of students. So you want to make sure you get that correct proportion there. So once we get that, it's 0.567. That's our sample statistic. And then we compare that to our hypothesized parameter, which is just the same thing as the number that's given in the null hypothesis, which happens to be 0.50. And then from a randomization distribution, we got a standard error. I didn't show it here, but I got it from a distribution in StatKey. So our standard error here is 0.022. And then just to find our test statistic, we do the p-hat minus the hypothesis parameter, and then we divide that by the standard error. So here our test statistic is 3.045. So step 3 is to determine the p-value. So we determine the p-value by constructing a normal distribution. So what we do is we take the test statistic and we plug it into the normal distribution, and that will give us a p-value from that. So we have the p-value of 0.0011634. That's what if you see in the bottom right corner there, that's where we got it once we plugged it into plugged the test statistic into the normal distribution. So then it's just similar as the other hypothesis test we did, where we make a decision and then we state a real world conclusion once we get the p-value. So we know that our p-value is 0.0011. So that is obviously very much less than our alpha level, which is 0.05. So therefore, we will reject the null hypothesis, saying that our data is statistically significant. And then just to make a real-world conclusion to bring the example to life, kind of, so we can say that there is evidence that the proportion of all World Campus Stat 200 students who are female is greater than 0.50, since our p-value was less than our alpha level. Okay, so next we're going to go over confidence levels, confidence intervals with the normal distribution method. So in the normal distribution method with confidence intervals, the mean is equal to the sample statistic. In the hypothesis testing before, our mean was equal to the null parameter. So that's where these two differ. So here the mean is equal to the sample statistic. The standard deviation is equal to the standard error. The confidence interval will be the middle of that distribution. So for example, for a 95% confidence interval, we find the middle 95% of sampling distribution, and that will be our confidence interval. So this is a little bit of a review, but for a 95% confidence interval, it's the 95% rule, so it's just the sample statistic plus or minus 2 times standard error. And then for the general form of a confidence interval is the sample statistic plus or minus z star times standard error. And the z star multiplier, as it says below, it can just be found in the z distribution. So you have to find the z-score that represents the percentage that you're looking for here. So it would either be pretty much around 1, 2, or 3, depending on what you're looking for. So that's why for 95% it'll be 2, because that's just the z-star that we use for 95% confidence interval. So binomial probabilities, these are based off of binomial random variables, which are types of discrete random variables that just count how often a particular event occurs in a fixed number of trials. So there's 3 conditions that have to be met for a variable to be a binomial random variable. So 1, there's a fixed number of trials, or a fixed sample size. 2, the probability of success is the same in each trial, so it can't be different based on each type of trial. And 3, the trials are independent of one another, so one trial doesn't depend on the results of another trial. So I like to use an example of when you're flipping a coin. So if you think about it, if you were flipping a coin 10 times, for example, there's a fixed sample size of 10 times. The probability of success is the same on each trial because if you're flipping the same coin, you can go heads or tails the same amount of time. It's 0.50. And then the trials are just independent of one another. So if you flip heads on one turn, that doesn't necessarily mean that you're going to have heads or tails on the next one. It's the probability is still the same based on each trial. So mean and standard deviation. So the mean of a binomial random variable equals the sample size times the probability. And then the standard deviation of a binomial random variable is the square root of the sample size times probability times 1 minus the probability. So those are just formulas that you should jot down. And then I'll just go over an example of how you would see these formulas, for example. So the number of red flowered plants has a binomial distribution, and the sample size equals 5, and the probability equals 0.25. So to calculate the mean of this, you would take n times p. So that would just be 5 times 0.25, and your mean would equal 1.25. And then next you see the formula for the standard deviation. So you take the square root of the sample size, which is 5, times the probability, which is 0.25. And then you multiply that by 1 minus the probability. So that would be 0.75. And then once you get all those numbers together, you get 0.968, which is the standard deviation. Okay, so that was a lot of information, but we're going to do a review. If anyone has any questions, you can just let me know. But this is just determining the SAT math scores to separate the middle 95% of scores. So the notation in the first part, so for the SAT math scores, are N 500, 100. So that's 500 is just our sample statistic, and then 100 is our standard error here. So take a moment, go over those confidence intervals, and let me know if you get an answer. Okay, yes, so the answer is B. So here for the middle 95%, we will use a 95% rule. So our mean, we take our mean plus or minus 2 times the standard error, which is 100 here. And once we do all that math, we get 300 and 700. Those are our confidence intervals. So we know that the 95% of scores are between 300 and 700. So the next question. True or false, the central limit theorem states that if the sample size is sufficiently large, then the sampling distribution will be approximately normally distributed for many frequently tested statistics. Okay, good. That is true. Just remember that as sample size increases, the more normal your distribution will look. Good. So which of the following is not an example of a binomial random variable? So remember the three conditions that we discussed for something to be a binomial random variable. So the options are number of correct guesses out of 15 true or false questions when you randomly guess all answers, number of winning lottery tickets when you buy 20 tickets of a different kind, number of left-handers in a randomly selected sample of 500 unrelated people, and D, number of tails when flipping a coin 15 times. So read those over. Okay, so the correct answer here is B. So going over those conditions again, there must be a fixed number of trials, the probability of success must be the same on each trial, and the trials are independent of one another. So A, the number of correct guesses at true or false questions. So you randomly guess all answers. And so let's just go through the conditions. So there's a fixed number of trials. Yes, there's 15. Two, the probability of success is the same on each trial. Yes, true or false, there's 50% chance on each because you're randomly guessing. So there's 50% chance. And then the trials are independent of one another. Yes, because you're randomly guessing all of your answers, and one answer doesn't depend on the other. I'll skip B and I'll go over C. So the number of left-handers in a randomly selected sample of 500 unrelated people. There are a fixed number of trials. There's 500 unrelated people. The probability of success is the same. So since it's random, the probability of success is the same there. And then the trials are independent of one another. Since the word unrelated is used there, they're independent. And then for D, we already went over this example, so this one should have been pretty obvious, but there's a fixed number of 15 trials. The probability of success is the same. Heads or tails, 50%, and the trials are independent of one another because one flip doesn't affect the other. And then for B, going back, this is not an example of binomial random variable. So the number of winning lottery tickets when you buy 20 tickets of a different kind. So there are a fixed number of trials, that is true. 20 is our fixed sample size. The probability of success, however, is not the same on each trial since they are different lottery tickets for each. Winning, whether you win one lottery ticket on another doesn't affect the other one, but since they're different tickets, there's a different probability of success for each ticket. So that will be different. So if you bought tickets of all the same kind, then this would be a binomial random variable, but since they're different tickets, they're not. Okay, and I think there's one more. So in a very large class, each student flips a fair coin 10 times. The number of tails that each student observes is recorded. Compute the expected mean of that distribution. Here, n equals 10 and p equals 0.5. So just compute the mean here. Okay, yes, good. 5 is our answer here. So just to review, the mean is equal to the sample size times the probability. So here our sample size is 10 and our probability is 0.5. And when we multiply those together, we get 5. So that is all. If you have any questions, you can stay behind and let me know. Other than that, we are all done.